So here in lesson 3.2, we're going to more directly link spontaneity, free energy, with equilibrium. And so the question I'd like to consider right now is what is occurring from a free energy standpoint at equilibrium? And I want you guys to think back to our study of equilibrium. When a system is at equilibrium, what can you say about the forward and reverse reactions? Hopefully, what just popped into your mind is that the rates of them are equal, so there's no net movement in any direction. That sounds related to spontaneity, right? So at equilibrium, we can say that the reaction is not spontaneous in either direction. And another way to say that is the free energy of the system is neither positive nor negative, it's zero. So yeah, if the system is at equilibrium, there will not be a spontaneous reaction in either direction. If that's the case, we can say something else. At equilibrium, one thing you guys learned a while ago is that Q is equal to that equilibrium constant K. So we've got delta G equals 0 and Q equals KEQ. So let's think about what that does mathematically to this formula. We've got 0 equals delta G at standard state plus RT ln of Q, or sorry, ln of K, now that I've made that substitution. And if I just rearrange this a little bit, I can see that there's a direct relationship between standard state free energy and that equilibrium constant K. Just bring the RT ln K side, part over to the other side, which would make a negative, but I'm just going to write it over here for a little bit of ease. So yeah, if I know K, I can solve for the standard state free energy change. I can also rearrange this to solve for K. I can do so by dividing for both sides by negative RT. Now I've got that equal to the natural log of K. And so if I want to get just K equals, I can take the exponential of both sides. So in the end, I've got E to the power of standard free energy over RT. And that whole expression that E is being raised to would be negative, is equal to my equilibrium constant. So, you can kind of think about the steps that one can go through, starting with just some of those appendix values, like the, enthalpies, entropies, standard state free energies, and you can get from that information the equilibrium constant. So that's pretty powerful. So let's just kind of do a little bit of review now and think about the differences between these two terms, standard state free energy and non-standard state free energy. And the simple answer is, well, one's standard state, one's not, but it's so much deeper than that. So just kind of comparing and contrasting them. Standard state free energy really only depends on temperature. There's only one value for any particular reaction if it's kept at a constant temperature, specifically at 25 degrees C. That's for standard state free energy. But for non-standard state free energy, you could poise a system at any particular point. You could throw together whatever concentrations of X, Y, and Z, and wherever you're at, depending on those concentrations, is gonna shift towards equilibrium, whether that's left or right. So there are many, many possible values for non-standard state free energy. I could have a lot of X, a little of Z, a lot of X, a little of Z. I think that's what I just said. Similar amounts of both. Lots of possibilities there. So let's think about sort of how these are calculated. For standard state free energy, really all I need to calculate standard state free energy is those appendix values, like the free energies of formation or enthalpy or entropy data for reactions and products. To calculate non-standard state free energy, that means knowing that standard state free energy and calculating Q, so knowing concentrations of reactants and products. What do they tell us? Well, standard state free energy, it gives the spontaneity of the reaction, but only under those standard conditions. Whereas non-standard state free energy, uh, this gives the spontaneity of the reaction under any concentration pressure conditions. And the kind of cool way to think about this is it tells us which direction the reaction is going in. And finally, one other place to sort of compare here, what is the value of zero meaning? Well, for standard state free energy, you're really not very likely to see a standard state free energy at zero. There's like not reactions where it just kind of magically adds up to zero. But if your non-standard state free energy is zero, that has a very important meaning, just that the system is at equilibrium, which is not uncommon. And then finally, one last cool thing that we just demonstrated is that we can get equilibrium constants from standard state free energy and vice versa. So just to recap, there's a lot of equations in thermodynamics, and just to recap them and sort of how they fit all together, I think this slide is really useful. So we started out this chapter talking about entropy, and we went through the equation, or just talked about how in general, for any reaction, if we take the product's entropies, which are defined values that you can look up on tables, subtract the reactants, that gives us the entropy change of the reaction. Enthalpy, this was something actually introduced first semester, but similar idea. All reactions and products, all chemicals have defined enthalpies of formation, which is the energy change associated to form the chemical. And because they're kind of all defined in terms of the same baseline, we can take the products and subtract the sum of the reactants in a similar way mathematically to the entropy. Once we have the delta S and the delta H, that information can be combined to really get at that driving force, that free energy of this reaction. Both energy changes and entropy changes affect spontaneity of the reaction and free energy. And nice thing about this equation is that we can take into consideration temperature. This is an estimate because the delta H and the delta S will vary a little bit with temperature, but it's a pretty good estimate for calculating delta G at non-standard temperatures. But we can also calculate delta G, standard free energy change, using the free energies of formation in a similar way to what we did with the entropy and the enthalpy. And the difference here is that the impact of temperature not being at 298 K would be quite a bit bigger here. So you really only want to use this version of the, or this delta G equation, standard delta G equation, if you are at 298 Kelvin. But otherwise, they are giving you the same information. They're giving you that standard state free energy. And so if you calculate it both ways at 298 K, it should give you a very similar value. Now, if we're not at standard state concentrations or pressures, here's where you need to consider free energy, non-standard state free energy, and take into consideration that Q term, which we just went over. And from that equation, we derived that standard state free energy is very much mathematically related to the equilibrium constant, which is pretty cool. And that can be, that can be written in either to solve for K or to solve for delta G. So yeah, there's a lot going on here with these equations, but I think that they are very usable. And how they all fit together, I think that's the sort of big picture, the more challenging thing conceptually. So next up is a problem. We're going to practice using these equations again, looking at it a slightly different way. Here, the question is pretty simple. It just says calculate the equilibrium constant for this reaction. but compare 298K, 100K, 400K. Back when we studied equilibrium, you learned that temperature does affect the value of that constant. And so this is really just backing that up, and it's pretty cool.